today. And so we were talking about matched data, matched analyses and matching and what that's about. We're more talking about matching rather than matched analysis last time, and we'll talk about the analysis portion today. The labs are a little ahead of where I am right now, but we're going to kind of close that gap today, and we'll get back on schedule here. I just like talking to you all so much, so we're a little behind. So we talked about matching really as something that's used across study designs, and we said that it's this idea of kind of arranging an index and comparison group to have the exact confounder distribution that you want through this process of identifying the comparison people that are similar or the same to the index group people based on these confounding characteristics. So, and that happens in a case control study where you have cases and you go out and find controls that look a lot like them on the factors of interest. And in the cohort or trial type designs, it's really the exposure, the exposed. You're finding exposed and unexposed that kind of look the same on the features of interest. And there's a number of benefits for this. It could be a very efficient way to control for confounding, and you can have a big gain in confounding control. You could control for what I called complex confounders, where really you can kind of, if you control for household through matching, there's a whole lot of information that goes into what makes up a household. It's family, common family history, genetics, environmental exposures, whatever. That's all baked into the concept of household. And so if you can match on household, you're getting many birds with one stone. So that's what I call by the complex confounder control. And then with that also comes variable reduction. I didn't have to go measure the 1,000 things that makes your household your household. I just have the fact that you're in that same house. So matching can be a very, very powerful technique. And we talked about, this is really where we were ending off, was in the middle of talking about different methods for matching. There's kind of this individual matching and then frequency matching. And individual matching is where you're really recruiting in a very specific way, 1-to-1, 2-to-1, so forth, controls that look like your cases on the factors of interest. So here we had sex, age, and race. And we were really very specifically finding matches for specific cases. Whereas in the frequency matching situation, they're really generally matching the distribution of the confounders and the control group to that of the case group, or the exposed and unexposed. So you're not necessarily recruiting a specific, hey, you this control, you go with that case, but rather in a general sense constructing your controls to match that of the cases. And so I had a few questions at the end of the last class about, well, I think it was me on the next slide even, I talked about, it's somewhere in here. But basically, you don't have to there's other ways to even, this is it. I said independently set the distribution. So what I meant by this was, here in this example, there's 3 variables, sex, age, and race. And here we have exactly that 12% of the cases are female, young, purple, let's say. And then therefore, we're going to go find 12% of our controls to exactly have that intersection of features. There's other ways to think about this. You could have independently looked at the sex distribution and said, well, it's about 60-40 male-female. Let's make our comparison group 60-40 male-female. And then I could have looked at age and I could have looked at race as separate entities and tried to generally balance on all 3 of those independently. So that's another way to even think about this. There's no rules to this, but these are all ways to think about matching in a group-wise kind of way. Obviously, you lose a little bit of something when you're independently coming up with the matching, rather than jointly thinking about all 3 of them in the way that this example has. So, in choosing all of this, it's about convenience and what's possible in your study design, in your situation. If you're, what the availability of controls is, and I think this is just it's an operational choice, and I'm trying to get us to analysis here, so we're going to jump through this. I think another piece to think about is that when we talk about in the language of matching, a question that comes up is how many controls do we match to each case? So in the examples that we all did in the spring, we were generally thinking about one-to-one matching, where you have one control per case. But you can imagine that cases in the case control designer, they're the rare limiting thing. You have 15 people sick with X, and you're trying to quickly figure out what is causing X. And so what you may have a lot of at your disposal are controls, right? These 15 people exist in a community, they exist in a hospital, or the church picnic, or whatever the examples we like using. And you may have more controls available to you to match to those cases. And so you might entertain other designs, such as R-to-1, which we mean let's say R is the number of controls. Let's say 4 controls or 5 controls per case. Or you might consider Ri-to-1, which means for one case I found 3 controls. For another case, I found 5, and you might vary the number of controls per case depending on what you are able to do. You may not always find enough. You have actual recruitment limitations, and you may not actually identify the same number of controls per case. Or you might see other designs where you maybe do have 2 cases. Let's say this is what this S means, S sub I. You may have multiple cases matched to multiple controls. So you can imagine there's any of these types of situations. Usually what you'll see is maybe 1-to-1 or Ri-to-1, where you have either exactly 1 control or as many as you could find per case, per one case. And again, this is really dependent on the specific situation that you have. The benefit of having more controls per case is you're getting more data. You have more of a sample size, right? Why in your pair match tables have just 2 individuals, as we'll go over the pair match table kind of layout, but maybe you can get 4 or 5 people in one table to make to do your stratified analysis on, let's say. And so there's a gain in precision in including more controls per case. But the thing is that actually it's a diminishing returns. If I went and recruited 1 million controls per case, that probably wouldn't give me that much more over half a million controls per case. Right? There's some point at which adding more controls per case is of diminishing yield, and then we have this kind of rule of thumb in epidemiology that it's maybe once you hit about 4 or 5 controls per case, you start to really lose the efficiency. It's not as efficient to keep adding more controls per case, that you kind of maxed out what you can do on precision at that point. Again, nothing here is written in stone, but these are just some principles to think about. And when you think about should be matched, like I've suggested, there's a whole lot to think about with whether you match or not. I think the idea here is that you really want to match on strong potential confounders, where you really, and so such that matching on them will give you a big gain in confounding control and precision. If we didn't match on this, we'd just be stupid. We'd be missing the boat. We'd have a compromised analysis. We didn't match on household, we didn't match on hospital, or whatever it is. These big kind of elephants in the room that if we don't deal with them in the study design, we're gonna get the wrong answer. As I've suggested a number of times, matching has a lot of logistical overhead, right? And so you have to be able to actually find and establish those controls these matches before a study enrolls. Right, so you have to be able to have some sampling frame or some way to recruit those controls in a reasonable way, right? And so that may not always be possible in your situation, right? You may not have a directory of the sex, age, race, distribution of your community, let's say, but you may, if it's a hospital-based study and you have hospital records that you can comb through and identify controls from. Or maybe it's that you're putting out advertisements and saying, I need controls that look like this, and you get people that way. So there's many different implementation things to think about. But one piece that is very important in the logistics is this bullet down here about you can only match on things that you can ascertain before you actually enroll someone in your study, right? So I would really love to match somebody on blood glucose levels. Well, the problem is you can't get someone's blood glucose level without getting their blood, and getting their blood means they're enrolled in your study, which means you've already consented them, right? There's this whole long chain of things operationally that you would have had to do in order to get that strong confounder to match upon. And so certain factors that you would actually love to match on are just impossible given how we conduct human subjects research. So again, another thing to think about, so you probably cannot match on blood glucose level, at least in the design of the study. You may do some analytical, or you may deal with it in the analysis in some ways later, and you could even think of interesting matched analyses downstream, but in the design of the study, you can't match on a factor that requires enrolling the study. This last bullet, I think we're gonna definitely get back to later today, which is when you match on a factor, you are unable to assess its relationship to the exposure or disease process in the actual analysis. So there's this trade-off with when we match. It's a panacea in terms of beautiful confounding control. You eliminate confounding on that factor perfectly. You're guaranteed to, pretty much. But that comes at the expense of not being able to assess it in the analysis itself. So if you match on sex, age, or color, purple, green, as we had in those figures, we actually lose the ability to talk about those factors in the analysis. And we'll see how that works coming up. So really, the moral of the story is we should really match only on the strong risk factors that we think are going to be confounders and that we can feasibly match upon. So what do we do once we've done our study perfectly, and you fast forward a year, 2 years, and now it's time to analyze it? What are we going to do with our matched data? And so there's kind of two, as we're seeing with everything in this course, there's kind of the previous way and the new way. And the previous way is thinking of this as a stratified analysis problem. And for that, we use Mantel-Hansel methods, and we talked about that in EPI 534 in some detail, and we're going to review that briefly today without all of the intermediate steps. So there's stratified analysis, table-based approaches to analyzing matched data. But we'll see that kind of breaks down, and we have to actually, it's limited. I don't say breaks down. It works, but in a very limited set of conditions. And to more deeply, to analyze more deeply, more complex situations involving matched data, we're going to need to use logistic regression methods. And so just as one quick snapshot of why we might want to use logistic regression, in the Mantel-Hansel methods, we were only able to deal with, in the analysis, the matched factors themselves for control. So if we matched on age, sex, and race, our analysis was limited to the control, the adjustment for the matching, which dealt with age, sex, and race. And that was, remember using the McNamara's odds ratio, which we showed was equivalent to the Mantel-Hansel odds ratio. But we cannot actually deal with factors not matched upon. But what if, as we suggested, let's say with blood glucose, or here we have blood pressure, BMI, activity level, other factors that you measured in the course of your study, you did your matching on age, sex, and race, you bring people in for your project, and you're measuring all sorts of interesting exposures and outcomes or whatever you're doing, and you might, along the way, collect some other stuff that you may decide you want to control for, such as these other factors here, none of which are really apparent at the matching level. I mean, you can maybe eyeball someone's BMI and say you look like a great control, but generally these are things that would have been ascertained in the conduct of the study. You can't deal with these really effectively at all in the stratified analysis, but in the logistic regression incarnation of this, we'll be able to. So that's really nice. And remember, a couple other things that we had talked about was that if you do a match design, you need to do a matched analysis. That's kind of the golden rule here. Match design, match analysis. If you don't, you are going to create problems which will appear as either bias problems or loss of precision problems, depending on the study design. And so you will induce problems that you don't need to be inducing by ignoring the match design in the analysis. And so in the pair matched situation, the individual kind of pair matched situation, we get data that looks in this kind of layout. So this is the layout that we're going to use on the upcoming slides. I don't know what happened to the rest of the unexposed here. But imagine we did a pair match study. We recruit a pair 4. And it's a case, let's say it was a case control study. The data layout looks something like this. We get tables that have just 2 people in them, because it's a pair match study. And the rows sum up to 1, because there's 1 case and 1 control. And the type of data that we're looking at here are whether the case is exposed or unexposed, and the control is exposed or unexposed. So here in this, imagine you recruited pair 4. They're, let's say they're purple female briefcase carrying females, or as these little people here. This is pair 4, and in this case, the case was unexposed and the control was exposed. And in here, both the case and the control are exposed. So this is the type of data we're looking at, kind of these very restricted tables of very small numbers of people, and the rows are summing up to the number of cases and controls. In this situation, if these were both the same groups, let's say this was a purple briefcase female, and then let's say both pairs 4 and 6 met this criteria, we actually may even talk about pooling these match sets into one kind of mega stratum, right? Nothing actually differentiates the cases and the controls in this case if they actually were the same on all of their on the matching criteria. So if they all met these 3 demographic conditions, you may actually say, well, why don't we just put them together? And I'll show an example of that as well. So there's maybe an advantage to kind of putting those together. And you might say, well, how did that happen? Well, it might have been that pair 4 and pair 6 were recruited 3 months apart, right? So at the time when the first purple briefcase female was recruited, there was 1 control available, and then another case develops a little bit later, and that becomes pair 6. And so operationally, there may be this time lag or some actual reason why they were considered as separate entities, and we can later put them together. So that's actually, in fact, what I just said here. Of course, I keep preempting myself, which I did last time. But here's a situation where we might do that. So here, and imagine you have some cases up here, some diseased folks, and some controls over here on the bottom, undiseased folks. And this is the order in which they came in, 1 through 6. Note that groups, pairs 1 and 4 are effectively the same on the matching criteria, and same with 2, 3, 5, and 6. And so you may actually just consider these as 2 groups, 2 kind of mega groups in the analysis. So even though the study was conducted this way, this is actually analytically how we might better deal with it. Just to, again, get some more statistical precision by putting more people into one table. So that's this idea of pooling. And there's, if to the extent that they actually do match, and there's no reason why 1 and 4 should be in different groups, this makes a lot of sense. So we're going to talk about this in a moment when we talk about logistic regression for all of this. But the idea here is that, in theory, we know that we can do stratified, what we were formerly doing as stratified analyses with logistic regression. That's what we spent the last week and a half talking about. And so too, we could actually, in theory, construct a logistic regression model that mimicked the stratified analysis that we know from matched analysis. And I'm going to walk us through that in a better way in a moment. So when we did the last spring when we did matched analysis, we were thinking about the stratified approach mainly, and we saw that in the pair matched situation, there was really only 4 ways that this can go. When you have one case and one control, and you're considering who's exposed and unexposed, there's only 4 configurations, right? And we gave them letters, W, X, Y, Z. The W's were, in this configuration, where both the case and the control were exposed. Or you could have the Z's where both the case and the control were unexposed, which again, I'm sorry, I'm missing the rest of the top part here. So these are 2 extremes where both are exposed or both are unexposed. Those are kind of boring, right? They don't really tell us much about whether exposure is associated with being a case or not. Right? We did this case control study because we want to figure out is this exposure associated with being a case or not. So we could make some statement about the risk of being a case based on the exposure. And these are boring because they don't really give us any new information. They're both, the case and the control, both are the same. But what gets interesting is these X and the Y configurations where you have a case is exposed and a control's not, which would tell us, looks like there's some evidence that the cases tend to be more exposed than the control. And the opposite direction is the Y situation, where you have a case is unexposed and a control is exposed. And remember, this idea of the McNamara statistic is, and the odds ratio based on that was looking at the balance of the X's to the Y's. Right? If we have more of these situations, more cases that tend to be exposed instead of the controls relative to the reverse situation, that builds the evidence that the exposure is a risk factor for disease. And so it's the balance of these 2 that's interesting, and the other 2 are kind of boring because they're uninformative. The cases and the controls agree. Now, in the R-to-1 matching situation, the tables, there's many possible tables. There's not just this closed universe of 4 tables. And so here, imagine a 3-to-1 matching situation. You can get a table that looks like this. Right, 1 case, 3 controls, that's the 3-to-1. And you can get a case is exposed, and then you get, you have 2 controls that are exposed and 1 control that's unexposed. So this is, one of many tables that you can get depending on the different number of controls per case. And you don't have this simple closed solution. You can still use the Mantel-Hansel methods to analyze this kind of table, but the McNamara statistic that that I'll show in a slide or 2 only applies to the pair matching situation, which is exactly what we said here. So this is really the universe of things that we're talking about with the stratified approach to the case control analysis. And we showed in EPI 534 that these are all the same, actually, for the pair match situation, that the McNamara odds ratio is the Mantel-Hansel odds ratio that reduces to the same exact thing. And the example that, kind of a classic example for demonstrating this is this analysis by Breslow and Day of hormone replacement therapy in postmenopausal women being associated with endometrial cancer. And there were a number of studies that went on, this is in the 70s and in the 80s, looking at hormone replacement therapy in a variety of gynecological cancers. And this one's looking at endometrial cancer. And here, the exposure among 63 pairs was estrogen hormone replacement therapy, and then cancer case status is the outcome. And then we have several matching factors: age, marital status, and then date of entrance to the community. So kind of another time-based control factor. And so here we have 63 pairs. Exposure is hormone replacement therapy. Outcome is cancer, and cancer case. And what you get is the data set that looked like this, where we have 27 pairs where both the case and the control are exposed. 4 where neither were, so you can just get a sense this is very prevalent. This is a very prevalent therapy at the time. And because we have 27 situations where both the case and the control are exposed. And then here, you see that 29 pairs of women have a situation where the case is exposed and the control is not. And then only 3 in the opposite situation where the control was exposed, but the cancer case was unexposed. And so this, you should just eyeball this and say, that's quite an imbalance. We have 29 saying yay association and 3 tables saying nay to the association. And so there's this tug of war, there's this tension between these two, and that's formalized by the Mantel-Hansel or McNamara odds ratio. This is really the McNamara formulation of it, which is x over y. So that tension between the 29 and the 3 is actually formalized as 29 divided by 3, gives you the odds ratio for the association between the exposure and disease. And the way to summarize those we had 4 tables previously. We said this is the number of W's, the number of X's, the number of Y's, and the number of Z's. We also can summarize it in this layout where we have, this is a different 2x2 table. We love 2x2 tables. This is a different 2x2 table. This one has not individuals representing each unit in the cells, but each one represents a pair. And this is a way to summarize the number of WXYZ pairs. Right, so the W's were where the case and the control are both exposed. The Z's were the number of cases and controls that were unexposed. And then the X's and the Y's can be populated in here. So this is just another shorthand way to summarize the 4 tables we had before. You didn't have to do this. You didn't have to make this in order to use these formulas. But this is a convenient way of summarizing the group experience into a single summary. And so that X over Y tension is the matched odds ratio over here. And similarly, there's a chi-square statistic, which is X minus Y squared over X plus Y, which is gives you the test of whether the odds ratio is equal to 1 or not, that null hypothesis of equals 1, versus the alternative of not equals 1. And then here we also had a formula for the confidence interval. This is the 95% confidence interval for the odds ratio. Okay, so this is all the McNamara formulation of the Mantel-Hansel statistic that you would compute on these stratified tables. And so what this turns out here's what you get for the specific endometrial cancer example. We have this 29 versus 3, which gives you an odds ratio of 9.67, so a strongly positive association between exposure and disease. And here we see it gives you a chi-square statistic with 21.1, otherwise known as highly significant because this is a chi-square with 1 degree of freedom distribution, and this would be a highly significant p-value. And so, and we also have a confidence interval that's rather wide between 3 and 32. Okay, so this is all old hat. This is what we did previously. I just threw up some SAS code here. I actually put this is on Blackboard. It's in the SAS code area. But this is actually how you might want to conduct this kind of analysis in SAS, which might be of interest to you. And here I'm actually showing it for homework 2. So that might be of more interest. And this is from question 10. So an easy way to do this analysis in SAS is you got to actually make pair match. If I gave you summary data, you have to make pair matched. You have to make individual responses that match kind of this pair match situation. So if I gave you a WXYZ kind of layout table, you have to make individual responses in a data set in SAS in order to actually analyze the data. SAS does not natively take this format. It does not care for your pair matched data, where one unit represents 2 people. It doesn't want that. It actually wants respondents. And so here's a little quick way to do this, where you can plug in a WXYZ, and then here what I'm doing is outputting 2 observations per per one, here, let's say this is looping, this is a do loop. Do people know do loops? You do loops. Okay, good. So here, if I have 2, W is 2, it's going to do this, run this code twice. From 1 to 2, it's going to make 2 people. So it's going to make 4 people for 2 matched pairs, where while you have a case and the control are both exposed, basically, is what is what we're doing. So everyone's exposed. The case 1 and case 0 represents case and control status, and they're both exposed, is what it's doing. And then it's stamping each record with this thing called stratum. And so the first folks are going to be called stratum 1, and then 1, and then 2, and then 2. And it's basically an ID number that represents the stratum. Okay, so this is how, I've done this for you, so you don't have to think about it too much harder again. But this is how you might want to do this in SAS to make individual level responses. So what it's doing is it's going all the way. You can look at what the do is doing here, as it were, but it's basically it's counting all the way upwards the number of people and looping through and making all of our W, X's, Y's, and Z's. Okay, and so here's some code for how you can do this in SAS, and this. It just should be familiar. We do tables stratum by case by exposure, and then you ask for the Mantel-Hansel statistic, and this is how you can get that odds ratio that we just saw. The X over Y type odds ratio is one. So if you have many strata, you're going to get a lot of output. So you're going to have to suppress some of the output or deal with your screen kind of going crazy for a while. And we're going to talk about this one in a moment, like now. Any questions on the stratified approach? Okay, logistic regression for matched analysis here. Okay, so we just saw all of this. We just saw this is the same example. These are the results that we got from the McNamara / Mantel-Hansel type approach. 9.67 is our odds ratio. But what if you got some extra data later? All right, you do your study and you start interviewing people. Now you ask them about start asking them about some other things, such as gallbladder disease history, which I believe is associated with endometrial cancer. And so now you might want to think of this potentially as a confounder, let's say. And so now this is a new piece of information that came along later. You did not match on it, and you would like to incorporate it into your analysis. So your data might look something like this, right? You have your first pair of women, case, control, exposed, unexposed, let's say, and now you've got this other thing, okay? This is the gallbladder disease history variable. Okay, so this is just the data is gonna come as you get it, and now you gotta deal with it, and it's not gonna follow this predictable case control pattern and this other exposure thing. You have this other variable you wanna deal with. How are we gonna do that? Okay, well, the problem here is that you can't do stratified analysis on this, right? When we can't, we have people that are, let's say in pair 1, they're discordant on, and in pair 2, they're discordant on this gallbladder disease status or disease history variable, and we cannot further stratify this table. I mean, we cannot further control within this pair for another factor. Right? We got 2 people in this table. That's problem A, and problem B we can't split them into further ways and think about further stratifying within that pair on gallbladder status. And maybe if it wasn't a pair matched analysis, maybe if there were like 15 people in a household, I'm trying to imagine what the senior community would be like, but you have some I don't know, if you had a larger group and you were somehow able to split them up based on their status and stratify within the larger unit, maybe. But the fact is, we just can't here. We have only 2 people, and they're discordant, and we can't really deal with this. So they're going to be dropped from the analysis if we try to even analyze gallbladder status. So we're going to look at how we're going to do logistic regression in this case. And so what we're going to do is modify the earlier EVW model And we're going to consider two types of V variables. The ones that we're not just going to be just confounders. We're going to distinguish between ones that represent like real, new confounders that we're analyzing, like gallbladder disease status. Let's say the actual things that we want to newly control for. But we're also going to account for membership in the match sets. Okay, because remember I said if we have a matched design, we still need to have a matched analysis, and our logistic model is going to need to deal with the matching. And we're going to represent that in these V1Is, and these are going to be dummy variables that represent the, what pair are you in, what household, what hospital, whatever we're matching on. And then the V2s are going to, V2Js, as it were, are going to be these other factors that we're accounting for kind of in the usual way, post, in the analysis, these are things we want to deal with way. And then the Ws we still have Ws, and they're usually going to be just the V2Js, just these other factors that came along later, like gallbladder status. So we're not really going to entertain effect modification on the match sets. That's just kind of odd, and we're not going to do that. And so we're going to get a logistic model now that looks like this. Okay, this looks a lot like the last version of the logistic regression model, except now instead of having a single sum of gamma times v's for all the I v's, or the k v's that you have, we're going to now have two groups of v's: the ones that pertain to matching and the ones that pertain not to matching, the other factors to control for. So this is just a slight modification of our model that distinguishes between these two types of control factors. Now, we added only v's, okay? And so if you remember, our formula for the odds ratio before that we talked about last lecture really pertains to, it was e to the beta plus the sum of all the deltas times w's. Remember that we only look at the pieces that are involved in product terms of the exposure, and those are the effect modifiers. And so our formula for the odds ratio from this model is actually the same, because we're only modifying how confounders are thought of, and like we said, all these v's just go away anyway in the odds ratio expression. And so this is effectively, this is really business as usual. Now, I want to just point out, and I think this feels a little funny, but notice that E here in this model, in our case control design, is actually kind of the outcome in a sense, right? You do a case control study. Well, case is really on the left. Whether you're a case, that's your disease. That's on the left side of the equal sign. And the exposure, in a sense, is the outcome, right? The thing you set about in your study to discover in a case control study is actually the exposure status. But despite that, we still actually maintain this orientation of the model. So we're predicting case status, which might feel weird because we already know who is a case. We recruited you based on whether you're a case or a control, right? We already know, let's say if it's a one-to-one design, we know half the people are cases and half the people are controls. There's no surprise there. That being said, we're estimating the odds ratio, that association between exposure and disease. Oops, sorry. And so just something to keep in mind. We're not going to change our usual approach, but just know that in the case control design where we're playing it backwards, we're still keeping the model orientation the same. Okay, so given what I just said, can you use this model to obtain the probability of disease in a case control design? In a one-to-one design, in a one-to-one matching case control design, do you need a logistic regression model to figure out the probability of disease? No, it's 50%. That's it. It is, right? It is 50% because your study design made it that way. You have decreed it to be 50%. Sorry, my phone is going crazy. And so this is, I think, a principle that you've seen before in other courses where the case control design is about measuring the exposure-disease relationship. It is not set up for figuring out the risk of disease. It is not, you cannot figure out the risk. You can maybe aspire to the relative risk through the use of the odds ratio, right? And we're not going to go into all of the thinking behind that because you've had that several times before. But we want to measure the odds ratio because we would like to talk about the relative risk. We cannot measure the probability of disease. And similarly, our model just can't handle that. And so there's really two flavors of logistic regression, as we've said before. What we've only talked about to date is the unconditional model, where we have, this is a more typical modeling situation. And in the unconditional model, we use it where we have the number of p parameters is small relative to the number of observations. Okay, so like let's say we had just a standard analysis here. Let's say we had an analysis with a study with 200 peoples. Let's say it says here a case control study, doesn't have to be. It can be any study. You have 200 subjects. There's no matching. And you're just doing an analysis of the association between exposure and disease with controlling for age, sex, and race. And here, let's say we had 5 parameters. There's 5 terms in the model. This means we have the p is small relative to n. 5 parameters, 200 people. And in this case, we would use an unconditional model. Okay, this is a poster situation for using the unconditional model. A few number of terms relative to the number of subjects. Compare that to this other situation. What if we had a similar version of the study that was pair matched? Okay, we did a variation of the same idea, 200 subjects, and we pair matched them based on their combinations of age, sex, and race. Okay, so 2 versions of the same study. One is we did no matching, and we just control for these things in the model. We just threw them in the model. What's your age? What's your sex? What's your race? And then put in the model. Here, it's in the matching. It's in the match design. Well, the model down here, corresponding to the matched model formula of the model that we just showed, would look something like this: alpha plus beta times exposure plus 99 dummy variables to tell us which of the 100 pairs you're in. So that's a lot of variables, right? 99, we had 100 pairs, so we're going to use 99 dummy variables to represent that. That's 101 terms in your model for your poor 200 subjects. That's a lot. That's that should make you upset, right? You don't want do you know how long it's going to take you to type that on the model line in SAS? And if it's going to go all the way to the right for a while, right? And you're not going to be happy that you have to do that. So that should feel wrong. You don't want to do that. So we're going to invoke what we're going to call the conditional logistic regression model, which is going to stratify on the pairs, and it's going to kind of, in a sense, remove it from the model. Okay? So if you fit this thing with an unconditional model, if you did fit this, you typed all this on the model line and you fit that, you will probably get a crazy answer, or you'll get a biased answer. You are fitting way too many terms in your model relative to the number of subjects. So you will get, right? But if you do the conditional model, you will get an unbiased answer. However, the gain in bias comes at a cost of precision, which is that the conditional logistic regression is often a less powerful technique statistically. You will get wider confidence intervals, often really wider. Okay, but at least you are not getting the wrong answer. You're just getting a wider interval around the right answer. So this is where you have to, in certain situations you may have to make this call. But generally, if you're looking at pair matched data, for sure, you're going to want to use the conditional logistic regression model. You're not going to fit a standard logistic regression model when you have this kind of matching. Okay, so what do we mean by the conditional model? More formally, when we're considering this thing on the right column here, when we have pair match data, The conditional model is going to give you the correct odds ratio, and I said it's going to give you a wrong answer. It's specifically, you're going to get the square of the right answer if you use the unconditional model. Okay, and so if I fit this in a regular proc logistic, I'm going to get the square of the correct answer. Not good. Okay, so I'm going to now walk through the kind of the conditional analysis using our gallbladder example. And so here we have our endometrial cancer folks who are matched on age, marital status, date of entry into community, and then not matched on disease history. For gallbladder disease history, we're just going to control for it in the analysis. This is all kind of, in a sense, baked into what it means to be in a given pair. And so the way we're going to control for all of this in the model is, again, by controlling just on the pair itself, on the ID number for which matched pair you're in. So age, marital status, entry into community are not going to be explicitly controlled for, but they're just going to be in, okay, you are in pair 17, congratulations, that means you are this age, this marital status, etc., based on how we recruited you. That's going to be kind of all baked into here, whereas delta 21 times gall, which is the gallbladder disease history, is an actual standard kind of thing that we would control for in the model. This says new because the old version of the slides had an I here instead of a 1. So if there's an I, just like connect the dot to the I and then you're set. So, so in this model, we have, we said there were 63 pairs, so 6 pairs means 2, so there's 126 individuals. And here we see we have an alpha, a beta, 62 deltas, and another delta over here, delta 2,1. That's 65 terms, and we're going to want to use conditional logistic regression. We're not going to want to use the unconditional model, which is going to require, the unconditional model is going to explicitly fit 65 terms to your 126 observations, then that's not cool. We're not going to want to do that. We're going to want these to go away. And the conditional model is going to make these go away by doing the analysis conditional and stratifying, in a sense, on all of these pairs. And so when we do this, we're going to get the e to the beta. I'm sorry here. I am.
Important to see at home.
There's something at home here. Terribly sorry.
You want me to say something?
Say something.
Let me just point out that Eli was talking about the conditional model. He actually is talking about the model up there on the top is the same model. It's one model you're using. What you're using is 2 different ways to estimate the parameters in that model. One method is called unconditional estimation, and the other method is called conditional estimation. So the model is the same, whether you're doing conditional or unconditional. That's the model at the top of the screen here. Okay, that's the model you're using for either way. So, but what Eli is saying is that if you actually did the unconditional model for this matched data, you're going to get a biased answer for the odds ratio for the effective exposure. If you did the conditional model, you get an unbiased answer. So it's not really the conditional versus the unconditional estimation. Okay. So, and if you start talking about, well, what do you mean by unconditional versus conditional estimation? What are we talking about? He's still working on this. So what are we talking about? How do you estimate the parameters in a logistic model? How do you do that? This was something that we talked about the first day, or reviewed on the first day. How do you estimate the parameters in a model? You do what's called a certain estimation procedure. What's it called? Maximum likelihood, right? And the way you do maximum likelihood is somehow you get a computer program to get something called a likelihood function. Remember that? A likelihood function. And then you get the program to maximize the likelihood function and give you estimates for the maximized likelihood function. Well, it turns out that if you're doing unconditional maximum likelihood estimation, the likelihood function is not the same as the likelihood function for conditional.
That's why it's got a different name.
That's why it's got a different name. So what you're doing is you're doing two different approaches to getting an answer that's fitting a model. One approach is going to give you an unbiased answer, and the other approach is going to give you a biased answer. So if you do the unconditional approach when you do matching, you're using this model. If you're using a conditional approach, you're using this model. But you're going to get the wrong answer if you do the unconditional approach.
Baxter. Baby with a fever. I'm sorry.
With a fever.
I know. So, sorry. Sorry.
My baby is 45 years old.
But yeah, so 4-month-old with a fever. Sorry. Sorry. Okay. Okay. It was a disclosure of health information. I should tell the IRB. Sorry. Okay, so we're going to do the conditional model. And so, again, from this model here, regardless of whether it's really how we're asking SAS to do it, actually, we really want to get, we want the odds ratio, and we know that the V terms are going to cancel out conveniently when we take the ratio of the odds. And so the form of, an odds of, let's say, the odds ratio when we have effect modification, let's say in the model, would look something like this. We have delta 1 times exposure times gallbladder status now in the model. I'm showing a different model with effect modification, how things change. If we might consider exposure and gallbladder disease status, we can now make our usual kind of odds ratio expression, e to the beta hat plus delta 1 times gall. So here, so notice we've extended our usual kind of model stuff. It's business as usual. We just got these terms for the paired IDs in them. So really this is not, again, nothing's really changing here other than we've got these control factor. We have these dummy variables in here to represent the membership in the pairs. And we can add things like effect modification as usual with these other V variables that we've entered into the model. Okay, and so how are we going to go about doing this in SAS? We're going to use proc logistic, but we're going to now use something called the strata statement. And the strata statement is asking SAS to do conditional logistic regression. And the conditional logistic model under the hood is, in a sense, it's forming the likelihood separately for each stratum of data. It's basically when the expression, the probability-like looking mathematical expression is going to be the product of many, many, many small likelihoods for each stratum of the data. Okay, that's really what it's doing under the hood. It's not doing it's splitting. It is stratifying the data and making many, many small likelihoods out of it. In a sense, kind of conditioning. It's conditioning on which match set you're in. And so the strata statement is going to tell SAS, hey, what am I stratifying on? And what the answer to that is going to be, it's going to be on, in our case, pair ID. You're telling it to stratify on pair ID. And so the data layout, again, is going to look something like this. The required elements in your data are pair ID, or whatever identifies the strata, the case or the disease, and the exposure status. And then here come all the other stuff, the V2Is or V2Js, as it were, and the W terms, and all the other data that you collected is going to hang out, in our case, to the right over here. And what's nice here is you should probably also have a study ID to keep track of individuals. If you don't do that, you're going to get really confused later. So please do that anyway in your data. And so this, again, is the data layout that we're dealing with. And so in this case, in this endometrial cancer example, we hope we have 126 observations, because that's going to correspond to 63 pairs. So pair IDs 1 to 63 will be 126 people. And so this is what we do in SAS that's a little different. The model is going to look like this. Model case equals est in gall, and est is the estrogen exposure variable there, estrogen. Gall is gallbladder disease history. So that is in the model here. This is our exposure, and this is our V2-1. But here, not on the model line goes the pair ID. And so now SAS is going to do, it's going to switch the tracks from doing an unconditional model to the conditional model. And it's going to stratify on pair ID. And it's going to give you output that looks, kind of similar, but with one key difference. And so these two things are interchangeable. When you see this is going to tell us, okay, we have V1 matching type variable, dummy variables over here. And those are going to be called, those are the pair IDs, that's over here. And then we have a traditional kind of exposure variable and V variable that's delta 21 Gall. Okay, so this means the same as this. This is very different. Okay, the wrong way to do this is this. Don't do this. Okay, never do this. Okay, if you do class pair ID, what have you done? You're basically switching to a regular old unconditional model. Like you imagine you could have done something like this, and maybe more precisely this, right? Say, look, I want to control for all the pair IDs, make me 99 dummy variables. This actually would save you from typing 99 variables, right? 99 dummy variables on the model statement. This might be if I gave you this formula and said, if I gave you, oh no. Okay. So if I gave you this and said, put this into SAS, and you did this might be your first naive swing at this. You'd say, I want 63 or 62 dummy variables, and I want to represent this thing called pair ID. Put it in like this. Give me 62 dummy variables, please. This is going to run the unconditional model, and you will get a bias wrong. You will get the wrong answer, and your output just may look weird because you're going to have a lot of dummy variables represented in the output. So don't do that. I'm going to undo. Oh no, I can't even undo it. So you know what to do. Okay, so you have it in the straight-up statement. Okay, so you have straight-up pair ID. Give me est and Gall and all of that. So what's not in the output here? What's missing? Right, there's three types of variables on the right side of the equal sign: an exposure, a whole lot of V1 I's, and a V2 representing Gall. So all of the stuff, all the dummy variables representing the membership in the pairs is gone. And that's okay. You don't really miss them, do you? You don't really care about them. You wanted to control for them. The stratification means you stratify on them, but you cannot estimate their effects. But that's okay, because did you really care about a specific pair anyway? Did you really want to estimate the effect of being in, older woman couple 72? I mean, or no, there's not 72, 12, right? The specific effects of the strata, in a sense, we didn't care about. We needed a control for it because we matched on them, but we don't miss not being able to estimate a beta for pair number 17. We don't care, and that's okay, but when we've controlled for them. Because what we actually care about is this thing, right? We care about the exposure, right? So that's the actual thing that we care about. We want to get the odds ratio for est. So here the odds ratio it's just e to the beta, and it's 9.1. Okay, so this is an unbiased estimate of the odds ratio, controlling for gallbladder status and the matching. How do we know we actually controlled for the matching? Did SAS do anything different? Well, it told us it's conditional, so we're just going to have to trust it, I guess. It is. It says it's going to say conditional. There's also a table at the top that's going to say like number of strata. It's going to start giving you some information that will hopefully start to make you reassured that it did the right thing. It will tell you that it controlled for 62 strata and so forth. Yes?
Suppose you go back a couple of slides when you show
Yep.
when you show the computer code.
Wait, more back here?
There. Okay, that's the computer code that you would use if you were doing unconditional.
That's right.
Right?
Yep.
If you're going to do the thing unconditional, that would be the computer code. If you can use conditional, you would change class to strata.
Right.
And you put pair ID. So
that's right.
Right, that's what you originally had.
It wasn't letting me edit. Oh, now it's letting me edit. Yeah, that's right. So there you go.
And then you get rid of that. Okay, here's my question. Suppose you left out the straightest statement. At the first line, suppose you had the first line, but you left out the second line, and you put the third line in the run statement. What would happen? Are you doing conditional maximum likelihood estimation? What are you doing? You're doing unconditional, because there's no straightest statement. Are you doing the same thing that Eli was saying when you had that class statement with the pair ID? Are you doing that? So what model are you fitting?
Wrong thing.
You're fitting the wrong model, because what aren't you doing? You aren't controlling for the matching. You're actually doing and you're not controlling for the matching, so you're actually doing sort of a crude analysis on the effect of exposure. Not exactly crude, because you're adjusting for gallbladder status. But you're not doing the matching, so that would be the wrong model, right? So if you want to do the matched analysis, then you have to have that straighter statement in there. If you leave it out, you're not doing the matched analysis.
You will get the wrong answer.
You get the wrong answer.
You actually got not just like, and it's not like you failed to control for something. You will get just literally a weird number that is not the right answer, and you will be fired. So don't do that. Not by me, by not by Donald Trump or something. I hope not. I hope he's not in a position to. But anyway, all right. So there's another way to, we've talked about the, you can represent the data in some sense, right, through this WXYZ format. And so you can almost imagine, well, what if, right, what if I wanted to, what if I had this WXYZ format or this weighted kind of format here? This is actually a little bit different than WXYZ because we have, I'm representing the two W folks here as two different lines, and I say there's 27 people like this, and and then I have three Y folks that look like this that are, what if I had weighted data like that? What if I had this kind of weighted frequency data for my analysis? We've seen this actually earlier with unconditional logistic, where we had weighted kind of just frequency data where you don't have a lot of other covariates, and you're just trying to fit things to this, to just aggregate data. And we've seen how to do this in proc-freq and in proc-logistic, where you can do, we called it event trials, for example, in proc-logistic. Well, this doesn't work with the straightest statement. This is the point of what this is to say. You can't really do the WXYZ, or this is a variation of it where you say I have 27 cases that look like this, 27 controls. You have to actually use respondent level data, like real deal respondent level data when you're using the straightest statement. You can't use weights. And so that code that I showed earlier about making a respondent level data set is really important for doing the conditional model. Okay, so SAS is just, if you say, like, if you have a weight statement, so Logistic itself has a weight statement, which lets you put in something like there's 27 like this and 3 like that. It will die if you put that in also with strata. Like, it's just going to give you an error message, and yeah. So I just want to point out a few other things. I'm going to run through these. There's like 3 other issues in matched analysis. They've actually pretty much all come up so far. Things to keep in mind, things to look at home, because I want to give this guy a chance to talk. He's already had his chance, but I'm give him one more chance today. And one is interaction involving the matching variables themselves. And so what I'm going to put up here like this is, what if we had a study where we matched on sex, age, and race? These folks come here again. So we have pair 1, and there are 2 green women on skateboards, and it's all of this. And what if we wanted to, specifically, look at here's our matched. What if we wanted to look at the disease, the case, and sex association specifically? Okay, not the exposure. or I'll just walk through this here. We have the disease-sex association. Every match set kind of looks like this, right? So here we have, we can't do much. This is the pair ID 1. They're both female. And so female, they're both female, and then they look like this. The case is female, the control is female. Here we have males. The males, the case and the control are both males, and so forth. So we cannot look at the association between sex and case status, right? This is part of what I was saying. You can't actually estimate stuff based on the factors you matched on. Right? We matched on sex, and now we cannot look at the association between case and sex because look, these are all those boring, uninformative tables, right? They're all W's and Z's, or and we can't do anything with them. And so you get something that looks like this. It's not going to be very interesting. Okay, so we can't look at the association between disease and the C variables, and we know that. Okay, but what about looking at effect modification? Okay, based on these matching factors. Okay, and so I'm going to just throw this up here. Okay, what about looking at the exposure-disease relationship across values of sex? And so here I'm not showing, there's no exposure represented in here. Okay, these graphics don't show exposure status. But what if in pair ID 1, the pair looked like this, where the case was not exposed and the control was. So this is one of those. This is one of the Y's where they're like this, the Y tables where it's going against the association. Here in pair ID 2, it looks like this, and so forth. You can imagine you could do this in your data, and then stratify it by what happens, the WXYZ tables, by whether it's male, whether you're looking at male or female matched pairs. Right? So you do your old analysis, but you can imagine, in a sense, what if I stratify this by male, female? Well, I could do that. No one said I couldn't do that. It's conceptually possible. I don't break up any, the tables have less data. But I can take all of the information after I match and then re-stratify, right? And so you can do that. We can do this in theory in our logistic regression model too. You could actually put in interaction terms with the matching factors, the factors that were matched upon. Okay, it's conceptually possible. It's not this situation where every pair is the same and you can't estimate everything. You could imagine effect modification, and we can deal with that. And you get a model that looks like this, where you have we have two sets of effect modifiers. One's involving the C variables that are used to match. So we have our traditional effect modifiers down below, and then ones that were part of matched sets. So you could have age and sex and so forth, and other effect modifying terms. So that's one way to think of this model. The problem with this is if I had an exposure by sex term in my model, I don't have sex alone in the model. Right? It was part of what went into the matching process. You were just pair ID 17 and you happened to be women, but I didn't control for sex as its own entity. And so that your inner statistician should be screaming in agony because you're not supposed to put higher order product interaction terms in the model without the lower order terms there. That's a problem, and that's what we call the model not being hierarchically well formulated. We're going to talk more about that in a lecture or two. So that you might get weird stuff because the model is not well done. The other one here is you could imagine effect. Okay, you can say, well, I'm not going to do that. I want to have the interaction between exposure and the dummy variables for the match sets, and that's just weird. You're not going to. We didn't care about the V variables themselves and the gammas that went with those, and we definitely don't. It's going to be very hard to deal with the EW terms. Okay, so the next thing is it's ignoring the matching. We don't encourage it. He said that already. And this is good. I would just look through this, and basically we shouldn't do it. You're going to get the wrong answer. Don't ignore the matching. Don't leave out the straightest statement. Breaking the matching, something else we don't encourage. This is Mr. Subliminal. Do you remember him? I don't know. This is like from like 1980s Saturday Night Live, but he would always say something else under his breath. I don't have time to do it now. But breaking the matching is something else that you shouldn't do. And then basically, it's you did a match study, and you controlled for age, sex, and whatever inside of the matching idea, the conceptualization of the matching, but then you ignore it and then just control for sex and age as regular old variables in the model. Right? You say, I did it in the design phase, I throw that away, and now I'm just going to put in a term for sex and a term for age or whatever. Don't do it. So, and this walks through where you can get some weird answers by doing that. Okay, and you've got 5 minutes.
5 minutes, let's see. I got less than 5 minutes. Oh, I got 5 minutes. Okay, here's what I'm going to do. Okay, we're done with this. Okay, even though you're not done with this, Eli went pretty quickly, right? You had heard this before, but when you heard it before last semester, I also went pretty quickly. So you're hearing it fast both times. Well, maybe both times. I don't know. I don't know what that means. Okay. So let's get out of this. Let me see. Don't save. Don't save. Okay. Let's keep that in there. And then let's go to, what happened? I want to go to this. Okay. So, got 5 minutes. Less than 5 minutes. Okay. I just want to start talking about, in just 4 minutes, what the next set of things we're going to be doing in the next couple of weeks. And we're going to be talking about this issue of what's called modeling strategy. Modeling strategy is a very important issue, and it doesn't necessarily relate to just doing logistic regression. It relates to any kind of modeling you're doing. It has to do with, given that you got a question, a research question, you got a whole bunch of variables, you have an outcome variable, you have an exposure, you may have more than one exposure, you have several variables you want to control for, you've decided you're going to use some kind of regression modeling, whether it's logistic regression or linear regression, which you've learned last semester, or survival analysis, which you're going to learn later this semester. You have this problem where you got a whole bunch of variables, you have a model, and you've got a question that you want to answer about the model or about the exposure variable, controlling for the other variables. How do you go about coming up with the right answer, the best model? How do you go about a strategy, or how do you go about the process of getting the right answer? Okay, that's what we're going to be talking about for the next couple of weeks. Okay, and what we're going to be doing as we talk about it, you're not really going to be learning any new things in terms of how to do certain tests or how to do, you're going to be learning sort of the idea of the strategy. And one of the issues in the strategy is, well, confounding. How do you assess confounding? When do you assess confounding? Another thing we're going to be learning is, well, where does interaction fit into this? How do you assess interaction in this complex strategy, and when do you do it? So that's what we're going to be doing. Now, the last thing I'm going to say is that I'm going to be giving you guidelines. The last thing I want to do is show you these pictures. Okay? Okay. Now, do you recognize anybody on this screen here? Anybody that you recognize? This guy over here, this is like 1980. Okay? So I had a beard. Okay? And in fact, in 1976, I had a bigger beard, and I looked like Charles Manson. Okay, so, but I wasn't Charles, you know. And this is my longtime colleague and friend, Larry Cooper, who is Kleinbaum, Cooper, Nizam, and Rosenberg. So that's Larry Cooper back in 1980. So who's this? Nathan Mantell. Who's Nathan Mantell? The famous Mantell Hansel. Mantell. And I'll start talking about the story next time, but it has to do with a meeting that Larry Cooper and I had with Nathan Mantell about talking about modeling strategy, trying to get the guru back then, he's still sort of a guru, but he's died, you know, trying to get the guru to tell us how to do modeling strategy. So I'll tell you the story next time. So we're done, okay? Thank you.
Sorry, try to...
That's okay. Good. So,